Welcome back to Linear Circuits. This is Dr. Ferry. This lesson is on AC circuit solution method. This particular lesson is the most important one in this module because we're going to finally be able to introduce a systematic way of solving circuit problems with AC inputs. Now, I've introduced this particular circuit several times, giving you motivation for why we want to go through phasors and impedances and define them. So we're going to finally show you how to actually solve a problem like this. We're going to be building upon phasors and impedances, but we're also going to go back to Module 2 when we looked at resistive circuit elements. And that particular module, we covered foundational methods and looking at how to analyze and combine series and parallel resistors using Kirchhoff's voltage laws, voltage divider, current divider, and we also introduced several systematic solution methods: mesh analysis, node analysis, Thevenin and Norton equivalents, and superposition. Now, it's important because when we did all of these methods, we were looking at purely resistive circuits. And when we introduced impedances, we said an impedance can be treated like a complex resistor. So in other words, we can apply all of these methods for AC analysis as long as we're willing to work with complex resistors. There's 3 steps to this method. The first step is to redraw the circuit, replacing all sources with their phasors and all components with their impedances. These are the impedances, equivalent impedances for a resistor, a capacitor, and an inductor. The next step is to use the circuit analysis methods that I just mentioned, KVL, node analysis, mesh analysis, to solve the circuit, treating the impedances like complex resistors. And the last step is to convert the output phasor to its sinusoidal equivalent. Now let's take a look at a simple example. This is an RC circuit. Step 1 of my method is to redraw this circuit, replacing the sources with their phasors. So this would be 2 at an angle of 30. And this resistor becomes 2000. So resistors, remember, stay the same. And this is Z sub C. And my output is the same. Z sub C is equal to 1 over j omega C, which is 1 over j. Omega is right here, is 2000. And C is 0.22 times 10 to the minus 6. And if I calculate that, I get 2272.7 over j. And if I multiply through by j over j, I can clear the j in the denominator. I'm going to have a j squared in the denominator, which is minus 1. So this is equivalent to minus 2272.7 j. So just a trick there, a j in the denominator can be replaced by a minus j in the numerator. So now I go back to this circuit, and I look at this circuit and say, well, how do I analyze this? Well, the method that I'm going to use is a voltage divider law. So this is really step 1 of my process. Step 2 of my process was to analyze the circuit. So I've got V out is equal to Z sub C over 2000 plus C sub C times the input, which is 2 at an angle of 30 degrees. Okay, so let me go ahead and substitute in Z sub C in there. I get minus 2272.7 j all over 2000 minus 2272.7 j at an angle, 2 times at an angle of 30. That's V out. So now it's just a matter of working with complex math. And your calculators might do this directly. So I won't go through too much of the details in here because I really like for you to be able to do complex algebra with your calculator. and different calculators do it different ways. So it's best to learn your particular calculator. But let me go through and just say, to convert from rectangular to polar, I would have this term in the denominator. And in the numerator, I've got a magnitude of 2272.7, and this is purely imaginary. And I've got a minus j in there. A minus j corresponds to an angle of minus 90. And then I've got 2 at an angle of 30 degrees. And the reason I converted all this to polar, because it turns out, as I've said before, it's easier to work with polar notation if I'm trying to multiply and divide these. So if I work through all this, I'm going to get 1.5 at an angle of, let me write as minus 41.3 plus 30 degrees, which reduces down to 1.5 at minus 11.3 degrees. So that's my final solution. If I go back to the last step, that is V out is equal 1.5 times the cosine of the same frequency, t minus 11.3 degrees. So that was the three-step process. Now I built this circuit, and I took the measurements of it. And here's the oscilloscope trace here. Now in our analysis, what we found is that with this input, we calculated this is a phasor of the output, or in terms of the cosine form, it looks like this. So the difference, phase difference between the input and the output was this one minus this one was minus 41.3 degrees. Difference between the input phasor and the output phasor. So going over here and looking at the plot, in green is V sub S, in blue is V out. And looking at this, let's see, this shows voltage peak to peak. That is twice the amplitude, 2 times the amplitude. And this again is 2 times the amplitude. This is the input, and this is the output amplitude. Because remember, blue is the output signal. So the input amplitude was 2, and the peak to peak is 4, so this is at 2 right here. So the peak to peak is from the bottom of the trough to the top. So this then is 1.5. Just looking at this plot and also verifying it from the peak to peak voltage. So when I built the circuit, I'm getting what I predicted I would get, which is very good in terms of the amplitudes. What about in terms of the phase? Well, from here to here, remember, is 360 degrees, and half that distance would be a delay of 180, and half of that is 90, half of that is about 45, and the peak is just to the left of 45. In other words, it's not quite 45 degrees, and if I measure this more carefully, I could figure out what that phase delay is. But from this plot, we're seeing this is minus 45. It's not quite 45, and that matches with what we calculated with the math, that it was minus 41. So in other words, you build this circuit, and the experimental result matches what you predicted by doing the analysis. So this particular lesson covered an impedance method for solving AC circuit problems. This particular lesson is the most important one in this entire module because it tells you how to solve circuit problems. We gave a three-step process. First, to redraw the circuit with its impedance equivalent. So we replace all circuit elements with their impedances, all sources with their phasors. We use standard circuit methods to solve node analysis, KVL, KCL, any of those methods. Just treat our impedance as if it was a complex resistor. And then finally, once we saw for the output phasor, we converted it to sinusoidal form. And what we also showed is that it matches with experimental results. In our next module, in our next lesson, we will cover a more detailed example of doing a circuit problem like this. All right, thank you.